Today we continuing, and yesterday we already demonstrated you some initial tool presentation of our model checker, which is being designed to support incremental verification. So our tool which you've been playing with is HiFrog. It widely uses SMT solving for various tasks. So let me get back to the picture to make sure everybody is back to speed. So yes, this is our infrastructure. Now it's a complete story. So, and it takes as input a program to be verified together with the properties we want to check that they are satisfied or not. And essentially the output of the tool is safe unsafe, meaning that the property holds, meaning safe, or property is violated, meaning unsafe. So when it's unsafe, it also generates as an output a counterexample demonstrating why the system failed. So in a nutshell, the user is completely out of the loop. The user just needs to provide the program to check and specify the properties to be checked, and then just run the tool. We had the demo and the interactive session with you, trying to involve you in the loop for you to understand better what exactly is happening, and consequently to appreciate the theory and the technology which we implemented and invented. So you already experimented with the fact that the program could be encoded into different logical representations, different SMT theories, and you can already experience the fact that for different theories, model checker performs differently, sometimes faster, sometimes slower, sometimes theory is simply not appropriate for the program to be verified. And then you have to try to figure out, at least as we shown it to you yesterday, you as a user should try to decide which theory is most appropriate. So then the other feature was construction and of what we call symbolic models of parts of the system. They are the summaries, function summaries, and they are automatically constructed for each safe run of the model checker. So we have a database of these summaries, which could be used to help us to get efficiency in when we're verifying the same system against different properties. And we already discussed the fact that these abstractions are over approximations. They could potentially introduce spurious behaviors. So then this spurious business must be analyzed by the tool. And if the tool detects that the summary is responsible for spurious failures, they are going to be refined. There is a block for summary refinement. So it's going to be recomputed, trying to remove the spurious behaviors and come up with a better candidate for the summarization. Additionally, as you already probably understood from overall presentation, so our framework allows to play with different encodings. So you don't have to use a particular encoding for the whole program. So you could decide to use for different fractions of the program different levels of encoding, different theories, and then ultimately you would try to use the encoding which is as cheap as possible to solve and to deal with. And it might be not appropriate, it might be not precise enough, so you would have to replace it later by something more precise, but potentially more expensive from the computational point of view. So, and there is this process which could be essentially automated, which is done in our tool. So we can actually modify some summaries, for example, if they are the level of encoding is not appropriate for the verification of task which we are doing. So you can convert one encoding into another, and the module which is called theory interface is exactly responsible for this. So theory interface will automatically convert one encoding into another while still preserving the abstractions. So essentially convert one summary into another. So this is overall picture. It's quite heavy, so to speak, because it's really tries to explain many different things which the tool is doing. And for this reason, there are so many arrows and going forth and back. So, but it's just the point for now, it's kind of a concluding remark to show you that it's a multifaceted tool. It has a lot of options. It has a lot of possibilities. And of course, we are trying not to involve the user to make the decisions, how to use it, what's best option for a particular benchmark. So the tool in principle is capable of figuring it out on its own. And we have some heuristics implemented already in the tool, which would help to do like all this different functionality to take a benefit of it for the best possible outcome. So, but what ultimately I really should point out is that we understand, yes, indeed, model checking, it takes time to make sure it's working for you. So sometimes it takes a lot of effort for the system to be verified. Even in a fully automated manner, something doesn't go through. So you have to tune the tool, you have to write defined parameters, you have to really make adjustments. And sometimes it takes an enormous amount of effort to try to verify a project, especially if it's a large project, if there are thousands of properties to be checked. So what our tool is trying to provide is the capability to remove this headache from the user. You do this, you live through this pain only once, and then once it's done for one property, so you have some useful artifacts created and remembered by the system, so they can be recycled later and not to repeat this pain for the second time. So today we are going to continue with HiFrog to show you some more features which you haven't seen yesterday because we ran out of time. So Sepideh prepared a very nice exercise for you to try to eventually appreciate the fact that everything could be fully automated by the tool and you don't really have to interfere. So, but first she will try to challenge you and make you suffer a little bit. So trying to figure out what's the best option to use. And then we will move on and talk about another tool, as I promised you. So this tool is called UpProver. So let me just move forward. So this is from the lectures. So it's a tool which has all the beauties of HiFrog. So but a little bit more. So it's now going to be able to verify not just a single system against many properties, but it will try to compare different systems and to see if the evolution of the system, if the upgrade of the system satisfies all the properties you already verified for the original system without spending months, and an enormous amount of effort trying to re-verify the system from scratch. So here's the conceptual, very quick overview of this solution. So having version 1, P1 on my slide. So we're verifying it and we collecting the summaries as the useful artifacts for the verification. So what happens if we have a new revision of the same system and we want to know if the properties are still true? So maybe the change was minor, maybe huge, but it's pretty much the properties are the same. You want to know are they still valid or not? And you don't want to re-verify the system. So what UpProver is doing, so first it's doing some different analysis on the syntactic level, identifying syntactically which parts of the system have been changed. And then for these changed parts, it will start revalidation of the summaries. So, and it's very obvious to some extent, maybe, is that sometimes revalidation of the summaries is sufficient to guarantee that the property still is satisfied for the new version of the system without running the overall verification loop. It might be a non-trivial task because the summaries could be quite involved and they could have a lot of dependencies. You really have to re-verify many summaries following the dependency analysis. So, but ultimately, we hope that it still could be localized with respect to the change and avoid re-verifying the whole system. And again, we are doing it. It's exactly what UpProver is doing, is summary revalidation. And if it finds that summaries are not valid, some of them just not working anymore, so the tool is going to repair the summaries. It will create new versions of them, which could be later used again for the new revision of the system. So you will never have to deal with revalidation of the system from scratch anymore. So that's the essence of the tool. So it's all, again, so at the end, it simply says, yes, system, the new version of the system is safe with respect to all the properties which you already established before for the original system, or it might find bugs and say, no, sorry, the change really caused the failure of the system. See what's going on. Your change is not good enough. So your old properties are now not holding anymore. So, but it's all localized. There is a question, so I need to see the chat room, I guess. So
No, I was just going to ask, when you say repair the summary, do you replace the summary in place and overwrite it, or do you keep both in case one or the other might be useful in the future?
Actually, here's the slide which illustrates it. So like here's, for example, my summary, right? And some block of it is not valid anymore. So we are going to figure out, through the code traversal, what exactly is happening. And it's going to try to go upwards in the call tree and revalidate the summaries above. And once it's been established, it's going to recompute. My screen again is frozen. So we had this in the previous session again. So the illustration was to show that, yes, we are going to discharge the old summaries. So you see they're crossed, and I will have a new storage. But now I'm going to have them recomputed. So but only locally for the old dependency fragment, which the change affected. So we are just going again, run an interpolation procedure, create a new interpolant, which will be the new summaries.
Okay,
So,
thank you.
yes, Mohammed.
Yeah, yeah. Is my understanding correct that basically you are saying that UpProver is strictly a superset of HiFrog? Is that correct?
Yes, HiFrog is the bootstrapping step of UpProver. So
Okay, right. So all functionality of HiFrog is already contained in, and additionally, if we want to verify a modification of the system, we can use UpProver.
Exactly. So
Right.
that's why I am presenting you two tools. So the reason is that they're not that different, except that UpProver is a, additional feature. So it really now takes as input two programs. It's not verifying a single system, it verifies two systems. And so today, in the second part of the lab, after we finish with HiFrog, we will move on to UpProver, and you will start exercising with verifying different versions of the system.
All right, thank you.
Okay. So we do have a lot of open challenges. Not everything is supported. There are many interesting tasks to work with us. We do have a lot of PhD positions open. Feel free to contact us if you're interested to collaborate. I will then pass my stage to Sepideh, and she will be starting the interactive session.
May I also ask a quick question before she sets
Yes.
up?
Yes, please.
So is it possible in the tool that we, if the property is not satisfied, so right, so we have a counterexample she showed yesterday, but is it possible to generate, let's say, a graph of that if the trace is very long? So instead of reading, so where did the program go and what was wrong with the program? So is it possible that for each line number, maybe by the help of a small graph, it shows that it went to line 17, 20, 30.
It's a very good question. Actually, in our early versions of this tool, we had a very nice GUI which was doing this. So it was visualizing the had graphical representations as a control flow graph. So the new revisions they became more involved, and we just ran out of time and didn't support the GUI anymore. So now it's not existent. So it's a possibility for somebody's joint work with us. We welcome it. So, but yeah, in principle, it's totally doable. So it's not so difficult. So, but the new revision of the tool doesn't have it.
Right. Thank you.
All right. Thank you for the questions. So if there are more later, don't hesitate to ask. So, and then I will then ask Sepideh to take over and start with HiFrog. And she really made a very nice exercise for you. So make sure the tool is running.
Hi everyone. So I'm happy here again to show some more interesting features of HiFrog. I think this is perfect time. We can see how summary and theory refinement works. So before that, I would like to kind of challenge you and to give you an exercise with an example that I will ask you to manually figure out what would be the right level of precision, right level of encoding for this file. So if you open this program, SMT-streamlined within the directory HiFrog demo. So as you see, there is a non-determinism here and some functions, and inside the main function, there are a bunch of assertions, 5 claims, and I would like you to check HiFrog for each claim separately and figure out what would be the cheapest possible encoding for each claim. For that, you may start checking HiFrog with QF-UF logic. And if it works, then yeah, you are done for that specific claim. But if it's not safe, so you know that this could be imprecise because of the abstract nature of UF, and you have to roll back to LRA. And if LRA gives you successful verification, then you can trust. But otherwise, if it's violated, you have to double check again with the propositional logic, which is the most precise but the most expensive theory. So I'll give you a couple of minutes and then we'll see together. Is the exercise clear?
Yeah.
So for the reminder, you may look HiFrog help messages by printing -h. That prints you all the options. But what you need for this specific exercise is this logic. For now, let's play with these 3 encoding: UF, LRA, and propositional. And again, remember to clean your environment. So there shouldn't be any old summaries from other benchmarks. Otherwise, it will interfere with the verification of this file. So for instance, for the first claim, what did you get by running with the QF-UF? Is it successful or the assertion was violated?
It is successful, I guess.
Okay, then yeah, for this claim, so we are done. So we know that UF is just enough to verify this assertion in the program. So let's move on for the second claim. So if you run, what would you get? Remember, again, you have to clean the summaries, because summaries was generated for that specific theory, and you cannot reuse it without adjusting to the new theory. Remember, each time when you switch to the new theory, you have to clean the repository. Any luck for checking the second claim?
So it fails.
Yes, it fails with the QFUF, right?
Yes, but it succeeds with the QF LRA.
Okay, then yes, UF is not the right choice for this claim. So you have to check more precise theory like LRA for that claim. And LRA, as you saw, it was enough. So again, for the other claims, you have to again start with UF. And if it was successful, you're done. But if it wasn't, you have to again check gradually, moving to the most precise one. But for instance, for the fifth claim, could you check that? What would be the right choice?
Sorry again, like which claim?
5, claim 5.
Hmm.
So if you run claim 5 with QFUF, what would you get?
I assume unsatisfiable, because with QFLRA, it's still
Yeah,
like there's a
exactly.
bug. Sorry.
Yes. Okay. Then yeah, even LRA is not enough for the claim 5. So your next choice would be propositional logic.
Yeah, it works with propositional.
So propositional work. The reason I gave this exercise was that you understand that how manual checking might be frustrating, especially if this size of the code is large and there are tons of assertions. So you couldn't check one by one and figure out what would be the right choice for each assertion. This is the point that I would like to draw your attention to use of a very nice option in the HiFrog, which is sum theorem. So let's use it together. If you type sum dash theorem like this, and you type the name of the file, then yeah, without specifying any logic, nothing, even no claim, just this. And if you run, you see that let's go back to the beginning, will automatically check each claim one by one, initial point. So when checking the first claim, UF is enough, and summary is also generated for the UF. Now, when it comes to checking the second claim, UF, you see that it gives SAT, and UF was not enough for checking this claim. So it rolls back to checking with the LRA. But here we have created a summary for the UF. So the tool automatically adjusts the summaries of the UF to be used also in the LRA. So it translates the UF summary to the LRA summary. And that's the box that you just saw in the architecture of the HiFrog. So there were a box of the theory interface that translates different summaries to each other. And here you can nicely reuse the summaries even between different theories.
But there's no
Yes.
smart way of it to like saying upfront, oh, I see the problem is of this shape, so I'll just immediately use the propositional encoding.
So if you try to use propositional for all of the
no. I was just thinking, I mean, here I can see, to me it seems like first it tries the cheapest and then it basically just goes down, but it has no logic to just see upfront saying, okay, this is a very hard problem. I need to immediately try with using the propositional encoding.
Like I suppose like you can do this, right, at some point, right?
Yeah, of course you can encode the whole program with propositional and check with that. But if you remember some of the benchmarks that we have.
No, that was what I was asking for. So what I asked for is like, if the prover could look at the problem and just already up front come up with the strategy and saying, okay, this problem probably requires this encoding, then it could go to the next one and just saying, instead of just trying, first using uninterpreted functions and then moving down the stack until it finds something that like solves the thing, then it could just say, okay, I can skip the first 4 layers and just go down to propositional logic in this case.
So could you elaborate what do you mean by seeing the code and figuring out upfront? Let's not talk about this toy example, but let's imagine there is a code with like hundred thousands of code. So then how would you understand that, okay, how the tool should understand upfront that for which assertion which would be enough? There should be some algorithm, right? You have to
definitely
encode. Yeah, you have to encode the program into some logical formula, and you have to try it. I don't think with just syntactical analysis of the program you can guess what would be enough, because there is really a dependency between the fraction of the program into the assertion. So basically the rest of the program just most of the time gets sliced out. You don't have to even encode. So the tool can identify that. So it takes all the codes that are dependent only for specific assertion and could only encode that part and then try something different encoding.
Could I ask a question about this? Like, how do you decide like the slicing? Like, essentially, you do reachability analysis until the assertion and say, okay, only this part of the graph is important.
Yes, yeah, exactly. Yeah, something like that. So you first create the single static assignment for the entire program, and then you slice out the rest of the program that it's not dependent to that particular assertion.
Okay. And can I have ask another question? How do you handle like more, let's say, static things that you cannot determine? Like, for example, like indirect calls or also like indirect jumps like this. Like, do you have like an algorithm for this as well, or you just simply, if you don't find a reachable path, you say, okay, yeah, you cannot reach this condition.
You mean if there are some instruction like go to in the C program?
Like go to or indirect calls, I assume like these things like you cannot 100% infer during static time, like just looking at the syntactic tree.
Yeah, absolutely. So that's what the C preprocessing of the C program does by UpProver. So when you take the C program as it is, let's say there are tons of go-tos, loops, if conditions, any usual C syntax, then the program is translated to some intermediate language. So it's basically compiled with the go to CC to and unrolled to an intermediate language, and then you have like an unrolled version of the program, and that is suitable for the verification.
Oh, okay.
I think what Victor means is if you have if you jump to some function based on input that you don't know.
Yeah, something that you can infer only after you run the program. Like, for example, if you have a function pointer and like you have an assertion in the function, but like this function is called through a pointer, you cannot actually reason okay, like there are some algorithms to kind of infer what functions may be called from an indirect side, but like you can't always tell for sure. So what happens like if you cannot find from the the start of the program until that assertion, because like the function isn't called directly within the code, it's like called through a function pointer.
Mm-hmm. Yeah, with the pointer, yeah, the story is different. So you need to have a specialized algorithm for the pointer analysis. But for the non-determinism, like here, so as you see, the value of the here, for instance, y, it takes any non-deterministic value. So you don't know what in the execution what y would be. So in each runtime, it can take any integer, right? What HiFrog does, it takes all the possible valuation of the y. And that's the beauty of the formal verification. So there is no execution there at all. So that's why the C program is symbolically executed. So it means that all the possible passes in the control flow of the program is modeled, and it turns to a logical formula. Then you reason into the logical formula. With this flow, you can really assure that for all the possible value, when you verify some assertion holds, you can guarantee that this is correct for 100%. But I agree that for the pointer analysis, when especially you want to dereference the pointers and you have a long trace into the heap, those we totally rely on SMT-prover. And if SMT-prover can encode this, so we will happily use it. Otherwise, if the assertion depends to the pointer analysis, we don't support that.
Okay, thank you.
I had a little question.
Sure.
Are the encodings, the logics that you support, presumably they're currently linearly ordered as far as more expensive, less expensive. But in the future, will it always be linearly ordered, or is it possible to be partially ordered?
That's a very nice question. Yeah, for instance, the order between UF LRA and propositional is obvious. But if you involve like LIA to this linear integer arithmetic, so I would say this is like there's not any more the linear order. So LIA and LRA could be like in parallel.
In that case, what would the sum, the THEOREF do? Would it pick one or the other?
In the current implementation of summary and theory refinement, the LIA theory is not supported, but yeah, the algorithmic level, it could be that you may try first LRA and then LIA or other way around. So there is no like definite order between these two theories.
Is there a reason LIA is not supported?
LIA is supported just recently, but this algorithm, was from like 2018, published.
It's because you don't have the translation.
Back then, we didn't have support for the LIA, and we didn't have the translation.
Okay, but you're working on this probably.
At the moment, we switched to the new tool, UpProver, which I'm really excited to reach there and to show some features of UpProver. But yeah, we will be happy.
It's on the to-do list.
If someone has idea, we collaborate to implement this. Okay, so let's close this story about summary and theory refinement. So I hope I convinced that this tool can nicely pick the lightest possible theory for each claim and automatically translate the summary when it's needed. And as you see in the repository, this time you generate more summaries because of the translation. So as an exercise, I would like you to check later to run another example for this, where you see also the counterexample, because sometimes it could be happen that all of the claims are not safe, and you will see also counterexample in the summary and theory finding. So if there aren't any question on this, I'm cleaning the repository for this, and we move on to other features. Yeah. I would like to show how we can tune the strengths of the summary. So if you go to the help message of HiFrog by typing -h almost in the end, so you'll see that for the ITP UF algorithm, you see 3 EUF interpolation algorithms. 0 stands for strong, 2 for weak, and 3 basically the combination of these two algorithms. Also for the LRA, we have like 5 interpolation algorithms implemented in the solver in OpenSMT. So these two are recently developed by Martin and published in TACAS 19 paper. You can go and check that out. This is a very nice algorithm for the interpolation. that generates interpolant in conjunctive form. That's why it's the most stronger interpolants, and that could be very useful in some scenarios, like especially in the PDR style model checking. Let's just quickly use this option in some benchmark. If you go to the commands provided to you, this one. So these are usual definition of the claim and the logic. And let's say I would like to generate interpolants with number 0, which is Farkas interpolation algorithm. And I'm using a verbose solver 2 that would print the interpolants in the standard output, and I can save the resulting summaries into a file. I'm calling it this time strong summary LRA, and the name of the function is this. If I run, let's see what happens. The result is successful, so I have proof of unsatisfiability, so we can generate interpolants using correct interpolation. And as you see, the resulting interpolant is printed here. Let's keep it somewhere. Remember, you see it's a or between two clauses. And let's change the interpolation algorithm this time to number 2. Everything else is the same. I'm just changing the interpolation algorithm for the LRA. And this is the dual version of the Farkas, which is weak, and that's why I'm calling it weak. And if I look up the printed interpolant, this one, let's put it side by side, we can see it. So which one do you think is weaker, this or this one? Yeah, this is printed in a prefix notation in the SMT lib2 format. So you might later write it down in a piece of paper, but I'm telling you that this has a single clause, so this is weaker than this. And in many cases in the HiFrog and sometimes in UpProver, this could be quite handy, because when the summary is weaker, so it could capture more behavior of the function, and you can reuse more summaries when you're using the weak summaries. Okay. I'm showing you one last features of HiFrog, and then we can close this discussion by HiFrog and we move on to the UpProver tool. So if you take this command here, I would like to focus to this option, reduce proof. So this proof reduction is used to compress the proof materials in the UF interpolants. So I'm using the interpolation algorithm for the UF, the strong one. And if I'm using the reduce proof, I will expect that the solver, the algorithm of the proof reduction could even further compress the interpolants, the size of the interpolants. So let's see. So I'm using the verbose 1 option, and it will print me some statistics about how much it managed to reduce the size of the proof and interpolant. If I run this command, yes, here you see the statistics on the reduction. These lines lists the important materials of the proof. For instance, number of nodes. The second column shows before reduction, and the third column shows after reduction. For instance, number of nodes before reduction was 145, but after reduction, it became 125. Decreased by 13%. And also the number of edges, you see a reduction there, and this shows the percentage. So this is very important that you could get smaller interpolants if you want to have. Any questions so far on HiFrog?
Why would you want smaller interpolants?
Smaller interpolants would benefit us. You can capture more behavior of the function. And then when you check if the interpolance is implied by the function, there is more possibility to go through. If you are interested in more detail of this, a colleague of mine, PhD thesis was exactly to study the different interpolation algorithms, and he combined different interpolants. So he had a thorough study on combination of different interpolants, and he compared the size and strength of different interpolants, and he managed to implement a flexible interpolants that you can really define on the fly and change the size and strength.
If I may add here, maybe to explain it a little bit easier. So essentially, it's very often that it ends up with having less iterations of the refinement. Remember, our system refines abstractions, right? So, and it could be a lengthy process. So a single refinement not necessarily solves the problem. The new candidate abstraction could be still spurious. So you might need another iteration and so on and so forth. So this ability to manipulate on the size and strength really helps to control this. So you might end up with a lot of efficiency gain when you have smaller interpolants.
Thank you.
Are they also by default easier to solve? Like if you use like smaller interpolants?
It really depends on the application. So it's unfortunately this is not a straight forward correlation between the size and the kind of property you're verifying. So we just observed in particular applications, you know, like in an upgrade checking, you want, for example, weaker and bigger interpolants, while in just incremental verification of HiFrog, it's better to have something more precise. So this like classifications which we observed and had proven. So, but it's also a lot of open questions here. If we could find a better characterization and exploit the flexibility better.
Thank you.
If there isn't any questions, I invite you to move to a new directory.
Maybe I have a question, a high-level question. I'm just wondering why in all the examples we don't have loops. So does this constraint make difficult the checking or not?
I think I am about to show you one example with the loop. Yeah, unfortunately I didn't have time to explain all of the features of the HiFrog, but this is very straightforward. You can, when you have an infinite loop, you can use a HiFrog and unwind option like this.
Okay, but the problem with loops, generally we need to provide an invariant. So is this the case for a HiFrog or not?
So here you don't have to provide invariants by the user. So you just specify the bound, and then HiFrog will create the logical formula up to that bound, and then it will run. And if the result is successful up to that bound, it will generate summary or invariant for you.
Okay, thank you.
So let's go to the UpProver demo directory. So here again, we collected some examples to demonstrate some nice features of UpProver. Just a recap that UpProver, this focuses on verifying revisions of the program. It will take two versions of program, version 1 and version 2, and after doing the difference checker analysis between two versions, it tries to incrementally verify the second revision based on the results of the first version. So let's demonstrate that feature. For that, we need to have bootstrapping check always. So let's run UpProver. So the name of the executable is just UpProver if you type. And here you can see also the help message of the UpProver. This time we mostly will work on bootstrapping option for the first version, running the UpProver against the first version to create the summary. And then for the second version, we will use this option, summary validation. Basically, it tries to validate the summaries of the old version and to check if it's still valid for the second version. So don't worry if it's not clear, so we will demonstrate with the example. So let's check the bootstrapping phase for one benchmark. Show you the benchmark first, version 1. Perhaps it's easier than both version in a diff, version 1 and version 2. So in the left, you see the first version. and in the right, the second version. As you see, these two versions are almost the same, except the return value in the function in the second version has changed from m to m+1. But the rest is the same. You see that it contains, again, some expensive operations that we really would like to avoid as much as possible, redoing the whole verification over and over again. Let's verify the first version and generate summary. That's what the bootstrapping phase means. UpProver version 1, and we have to use bootstrapping option and the logic. Let's take an array and let's run. Yeah, as you see, the verification was successful for the first version, and one summary has been generated. We can quickly take a look into the summary file. This is the summary for the function. You don't have to really understand. This is printed in this formula is in the SMT lib2 format, and it's created for the machine, not for the human. Yes. Okay. And now we have summary, and we verified successfully the first version. Now let's
Why did you
verify.
use LRA?
Just for the demonstration. So you
Okay.
can use other theories as well, because the assertion in the program could be verified easily with the LLM, but you are free to check other theories as well. Let's see. Let's just quickly see the summaries here, which is this one for that nonlinear multiplication. This time we see also second file, which is called Omega, but you don't have to really understand that. This is for mapping the two versions of the program, because we have to keep track of which function stayed the same. For instance, non-det function stayed the same, but func has changed. So these numbers, yeah, has meanings, and which had summary, which didn't have summary. We store all these informations. Now let's run. Sure.
So just for information and my knowledge, so these summaries that you showed and the Omega file, is there somewhere some documentation that you explain that what do these numbers represent? Just for curiosity, I mean, is there an explanation? Let's say there was 21. What does that represent? There was. Is there some explanation in some document available?
Documentation? No, actually, we intentionally didn't release that, because this is very technical information that we don't really require the user to understand those numbers. Those are like the ID of the summaries, and it's intentionally hidden. But if you are really interested to know, so you can send me an email and I can explain it offline.
Okay, sure.
Yeah.
Sure. Thank you.
Yeah. Now let's verify the second version. This time, so you have to delete the bootstrapping option, and this time you add summary validation that takes the argument that is second version, right? So what I'm doing now, if I run this command, let's see what happens. It takes both versions and it converts to the logical formula here. And you see that here you see that function main is preserved. Both non-det functions also preserved, but function func is unpreserved. And in total, we have one unpreserved function. And the diff time is, you see that it's very negligible for this benchmark. And the tool starts to check the old summary that existed in that file to check if that summary is valid for the changed function, for the function func. So it tries to validate, and as you see, the result is unset. It means the summary again is sufficient enough to capture the new changes of the second version. And here you see that validation is done without verifying the second version, without creating again whole formula for the entire version.
would it have been able to use a different logic in the summary validation?
At the moment, we are strict to use same theories for both bootstrapping phase and the summary validation. We don't have summary translation here. That would be one potential work to improve UpProver.
Are there pros and cons of using HiFrog instead of UpProver in Bootstrap mode, the Bootstrap option?
And it's exactly the same. So the bootstrapping is, it's basically running a standalone HiFrog run. So what the tool differs is actually in the second phase, in the summary validation. So if you run HiFrog for the second version, so again it will kind of do the bootstrapping for the second version, and it will create the logical formula for the entire program. But as we saw just here, that UpProver didn't do that. So basically, it took the old summaries and it tried to see if it's valid or not. And if it was valid, it means that this version is also safe.
Thanks.
So if this is clear, I would like to ask you to take the program from the SVComp 20 categories, the regression verification, and to run both bootstrapping phase for the first version and summary validation for the second version, and to see if you can find some useful summaries that can be successfully reused in the validation of the second version. Yeah, now it's your turn. Go ahead. And again, don't forget to clean your repository. Yeah, you have to also clean another file that starts again with double underscore. That's called Omega. UpProver generates this to map two versions of the program. So that's needed for the internal algorithm of the UpProver. So make sure that's also cleaned like summaries. The drivers video V1 is the first version that you would run the bootstrapping on. Yeah, one note here that this benchmark drivers video V1 has infinite loop, and you have to define some bound on it. So I recommend you to use unbind for. Anyone managed to run the bootstrapping phase?
Yes, but is the fact that it's, so I first did it without the unwind and it kept running.
Yes.
But is that, is it really a infinite loop in the program?
Yeah,
so
there is, this program has, I think if I remember, there is infinite
okay.
loop, so you have
so
to
it's not,
define.
so because the process keeps running, I could infer that maybe there is some infinite loop problem.
But I think it's on purpose.
If you see, that
driver,
something is.
so it should be non-terminating.
Yeah, if you see some specific function gets inlined and forever, and that's the sign of infinite loop. So you have to define a bound right there to stop. So did you manage to run with the bound?
Yes, it says warning claim is set to 1. Does that mean anything?
But what the tool does, it takes all the claims and conjoins all of them, because UpProver this time doesn't take any claim. You take all the existing assertions in the program and you focus on verifying different revisions. So in each version, you assume that all the assertions are same for every versions. I'm also running for the bootstrapping version. Did you also run for the second version, the summary validation phase? And try also record the time to see if the second version was quicker than the first one. For me, the bootstrapping phase took 20 seconds. And 331 summaries has been generated. Let's see if these summaries could be useful to verify the second version. Do you see any time difference in the second version?
I think it was faster. Like I didn't time it.
Okay, yeah, that's expected because
but
it starts.
I did it with another logic. So I just didn't give a logic. And then the first time it was the bootstrapping took 5 seconds and the validation took 9 seconds.
So it was UF, right?
Yeah, probably, yeah.
And both was, so the bootstrapping was successful? So if it wasn't successful, then because then the summary validation doesn't make sense because you have to have a summary.
It says verification successful.
And you had summaries there. So you could check the summary files and to see if the summary was generated. For instance, for my case, when I ran with LRA, you see that in the second version, so the difference is only in 12 functions, and 1,200 nodes were just preserved, and you don't have to really verify those functions unless it's really affected by the functions in the subtree. And the diff time is printed here. And after a couple of validation, the second version is also indicated as safe. And you see that at the time, this time is 8 seconds, so 3 times faster verifying the second version. Since we don't have much time, I would like also quickly show you one interesting scenario that could happen when you compare two versions. For instance, if you take GPU file, if you do the diff between two files, GPU version 1 and GPU version 2, so you will see that there are some differences syntactically in the files. Yeah, these are just the pre-processing, but yeah, there are some real differences in two versions. And if you run UpProver for the bootstrapping phase, this time with UF, and again with the unwinding 4, let's see what happens. Yeah, usually bootstrapping takes time because it has to generate summaries. We would like to know if the generated summaries is useful in the second version, and the tool also can repair the invalidated summaries. It was successful. So the symbolic execution time took 37 seconds, pretty long, and the total verification 45 seconds. So if I run the summary validation for the second version, let's see what happens. This is very interesting situation that you see that the number of changed functions is 0 and all the functions has been preserved. So as we saw just a minute ago that there were some syntactically difference between two versions, but what it happened that when you create an intermediate encoding of the program, two versions were semantically identical. That's why UpProver didn't do any summary validation because there weren't any changed function. Basically, the second version is also safe as first version. And here you see that the first run took like 40 seconds, but this time is just you invested on the diff analysis almost 40 times faster. So here incremental verification really pays off.
Sorry,
there are some yes.
I didn't get this diff time. So are you saying that this is the total time that it took for the validation, or is it the difference between the time of the first file and the second file?
Yes, that's a good question. So what UpProver algorithm does when it takes two versions, so it starts to compare function per function. So as you see here, it's printed. For instance, this function is preserved, this is preserved. So it keeps comparing two versions. And this would take some time, right? The time that took to check this diff analysis between two versions took 1.5 seconds. And since the tool didn't identify any changed function, so it doesn't see any reason to revalidate summaries because there is no change in the new version, right? So implicitly,
Right.
this version is safe.
If there was let's say a non-zero value of unpreserved nodes, so it would also report another time which it would have taken for the validation, right?
Exactly, like before.
Okay,
Yeah, previous example. Yeah, in the previous example we had some changed nodes, and we had time for validating, and time also for creating a new repaired summaries, because after each successful verification you create and repair invalidated summaries. So all these times also, yeah, will be printed in those cases. But for this benchmark, since it was identical, so none of them is necessary to be. And this is very nice. So there are like different types of changes that you can play with. For instance, in the second version, what if a new function gets introduced, or what if a function gets deleted in the second version, or if the signature of the function gets changed. In different scenarios, you will try to reuse the summaries. But at the moment, when the signature of the new version changes, we don't know how to use the summaries. For those cases, we just delete the old summaries. And this is one of the potential cases that if you are interested, you can work on and introduce your algorithm. If the structural changes between two versions is drastic, not local, then how we can make the most of function summaries from the first version. I also would like to just quickly tell that the interpolation algorithm that used in the UpProver is a specialized version of the Craig interpolant. Here, since you are taking a summary of the old version, old system, and trying to bring it back to match it to a new system, so you have to preserve some properties there. And we have published proof for this to guarantee the soundness of the UpProver algorithm. And the property that should preserve is called tree interpolation property. So you cannot use all the interpolation algorithms for the prover because it wouldn't be sound. At the moment, you can use a Farkash interpolation algorithm and decompose Farkash interpolation algorithm under some restrictions. The rest, if you really want to use those interpolation algorithms, so you have to check if that property, if the tree interpolation property is preserved in the summaries. And for that, we have implemented a on-the-fly check, which is called tree interpolation TIP check, that you can do the bootstrapping, you can generate the summary, and then you manually run this check over the summaries. And if it passes, then you know that the tree interpolation property is preserved and you are good to use the summaries in the second version. I think, yeah, it's time to finish if there isn't any more questions.
I have a last question if it's possible. Just
Yes.
with HiFrog and UpProver, we can verify, let's say, probabilistic systems. I mean, there is an extension for HiFrog to deal with the stochastics or probabilistic systems.
Unfortunately, not.
Okay, thank you so much.
Can I ask a question?
Sure.
So does HiFrog and UpProver also support liveness properties?
So if you encode the liveness properties as a assertion into the C program, yeah, you can encode, but you have to remember that the HiFrog is a bounded model checker. So what it gives us is always guarantees that up to a certain bound, it can prove that properties. So.
Oh, right. Yes.
Mm-hmm.
Okay, thank you.
So the question is, are there any tools that supports the rechecking the proof? You mean the validating the proof that has been produced by the solver? I think if the question is that, this is a quite nice and recent result by my colleague. He has recently published a paper in DAC 21, and you can check our website for that. So this is a still ongoing project, and he was trying to validate if the result is safe, result is unset coming from the OpenSMT, if it can be validated. Yeah, the paper is on the website.
Martin will send the link in the chat room.
So everyone take a 10-minute break, and then we'll start the next lab at about 10 minutes past the hour.
Thank you very much for the introduction. It was quite interesting for me, especially like I'm not that knowledgeable in this domain, so like it was interesting to learn new things.
Thank you for your interest, and thank you for good questions. So I think it was quite productive.
Thank you very much. It was very useful and very helpful.
Thank you.
Okay, thank you. So I will be happy to take your questions offline, and the sources are open in the GitHub. So feel free to take a look and contact us. So thank you very much. I hope you enjoyed it.
And yes, once again, we have a lot of open positions for PhD studies with us. Feel free to inquire. We will be happy to consider you.